All right, I want to look at roots, and we're going to play with an idea here that the square root of 2 is asking for two numbers when multiplied together equals 2. In fact, if we take the square root of 2 and multiply it by the square root of 2, we get 2. And that's going to be the key to help us redefine this symbol for square roots. And so what I'm going to do is I'm going to let it be something. I'm going to let it be 2 to some power. So I'm replacing the square root symbol with 2 to a power. And we know this is equal to 2 to the power of 1. Because it kind of, in our definition of what a square root does, we're asking for two of the same things when multiplied together to give me the answer. And so our rule of exponents says I have 2m plus m equals 2, 1, or 2 to the 2m equals 2, 1. These exponents have to equal. And m equals 1/2. And so we get this equivalence that root 2 is equal to 2 to the 1/2. We ask ourselves, well, why don't we look at other things? Let's look at the square root of x. That means we want the square root of x times the square root of x to equal x, or x to the 1/2 times x to the 1/2 equals x. And our rule of exponents says if we do add up these exponents, x to the first does equal x to the first. And so roots can be written as fractional exponents. Now what's really, really nice about this is that this gives us the ability then to use all of our rules of exponents again. Right? B to the 0th is 1, b to the negative mth is 1 over b to the mth, b to the m times b to the n is equal to b to the m plus n, b to the m over b to the n is equal to b to the m minus n, b to the m to the power of m, n is b to the m times n, and so on. This expression, then we can really do a nice thing. I could take the square root of x cubed and replace the square root with x cubed to the 1/2 power, or x to the 3/2. And so the only thing we need to recognize here is, does this extend? So if we look at the cube root of 2, we're asking ourselves cube root of 2 times cube root of 2 times cube root of 2 equals 2. So 2 to some power times 2 to the some power times 2 to the some power equals 2 to the first, 2 to the 3m, because m plus m plus m is 3m. And so m is equal to 1/3. And we now get this really nice relationship that anything to the nth root is the same as the 1/n root. And so I like, and it does become a lot easier when working with power rules, to have our square roots written as a power, because then we treat them like a power, a fractional power, a rational power. And so we can have a system where we have the square root of x squared minus b squared in the denominator of 2x. And if we translate this, we now have 2x over x squared minus b squared to the 1/2. And if we translate it further, 2x x squared minus b squared to the negative 1/2. And this is ripe for you substitution, because I can say, hey, u is equal to x squared minus b squared, so u is 2x dx, I'm sorry, du, and that means that this is part of the du, and this is u to the negative 1/2, or 1 over the square root of u. It lets us use our power rules. It lets us move things about. I again, because I used a Pythagorean example, and this pops up a lot in vector physics and systems. Being able to move about roots and multiple versions of roots work out well. And as we integrate and derive through these, we get meaning to things like a 3/2 power, which is, the cube of this. These are equivalent. This becomes harder to deal with if we treat rules for the square root symbolically as its own thing, but if we can combine it into a power, we already have the power rules.